So welcome to the XSEDE MPI workshop. I'm John Urbanek, coming to you from Pittsburgh Supercomputing Center. This is the workshop that most excites me as a parallel programmer, because this is the most powerful of all the parallel programming techniques. This is where we turn you into MPI programmers in the next couple of hours here. I think I made a persuasive case earlier about why we use MPI, why you should be excited about learning MPI, but I'll reiterate some of those points once more. First of all, it has been around a long time. It has been around now well over 25 years. And over that period of time, it has done nothing but mature and grow more dominant in the world of parallel programming. As I mentioned, it is now over 99% of the codes that are running on large HPC platforms are going to be MPI based. Because it's been around for such a long time, it's got such an established base, it's got so many codes, it's guaranteed to be around for a long time. As I mentioned earlier, the roadmaps for these exascale machines that are coming up now and are being developed in the near future are all built around the assumption that MPI will be the baseline programming method. There are lots of libraries and lots of algorithms that are built around MPI. It is extremely scalable. It is, I say 3 million cores there. I think the answer is actually over 7 million cores on the fastest machine, the biggest machine in the world right now. So it scales to millions of cores, literally. It is extremely portable. Every code that we're going to go over and we're going to cover in this next day and a half will work on your laptop equally well as on bridges, equally well as on any cluster you're going to find anywhere. The standard really pays a lot of attention to making sure everything is portable, and it works out that way in the real world. Codes just move around with zero issues is typical. Large, very complex codes. It works with hybrid models, by which I mean it interoperates with other methods of doing programming as well. Like, for example, MPI and OpenACC interoperate very well if you want to do parallel programming on GPUs across a large machine. We'll talk a good bit more about hybrid programming for our advanced MPI when we get there. But it absolutely is. Other programming models have to work well with MPI because it is such a standard. And that's all we're going to say about it right now, because until you actually start doing some of the stuff, these are just bullets. They'll become much more meaningful after we start to do some coding. So let's start to do some coding here. We're going to need some basic capabilities here, and MPI is going to provide them, and it does it through a model that is very straightforward and simple and easy to wrap your head around when you're using it. So let's define MPI first. It's called the Message Passing Interface Standard. And it's a library that allows us to do problems in parallel using message passing to communicate between processes. That's a loaded sentence. It's got some terms in there. First of all, it is a library. It's not a package or a language that's a thing into itself. There are lots of other parallel programming approaches that start out and say, I'm going to write the perfect parallel programming language. That's not the case here at all. It is simply a library that you can use with very standard C or C++ or Fortran. And there are lots of other extensions too, but it is a standard library, like a math library or graphics library. It is no different, and that means you get to retain all the knowledge that you already have about your language, and that's quite important, because in reality, anytime you change a language and you extend it to make it a parallel language, there are a lot of subtleties and corner cases and odd things that just come along with that transformation. The fact that MPI says that I'm a library means you get to still retain all of the standards, so you can get your C book out, your C knowledge out, your C Bible or specifications out, and be sure that they apply precisely to what we're about to do. We say it's message passing. What does message passing mean in general? A lot of people will just say, oh, it's a paradigm like that says anything meaningful. What it explicitly means, and what you're going to shortly see, is it just means we're passing chunks of data back and forth. In large scientific codes, these will be sections of an array. We're just sending pieces of data back and forth between our individual processors. We say we communicate. Nice thing about MPI is it hides all of our communication, so we don't care whether we're using a really fancy MPP, 3D torus network or fat tree, or simply some cluster that you cobble together yourself with your office network. MPI is going to hide all of that from us. That is a very nice thing. It helps with portability, it helps with programming. The last part of that sentence that's important is we talk about communicating between processes. And so when we're talking about a process on either a Unix machine, where it's very clearly defined what a process is, it's those things that show up when you type PS and it lists all the processes, or on a Windows laptop, where it's those things that show up when you fire up the task manager and you list all the processes that are there. That's what MPI communicates between. It's just a process. It doesn't actually require separate physical processors and cores to be involved. It can be any one of those processes. And if you have a Windows box, for example, that if you pull up the task manager, you'll see that there are probably around 100 processes running at any point in time. You don't have 100 cores on your laptop. So those processes are really separate software threads that are just running and swapping in and out with the physical processors as things run. Same as on any Unix machine. So if you've got a Linux laptop in front of you right now and you list all the processes, there are, again, roughly probably 100 processes running on your laptop. And even though your laptop might have 4 cores or 6 cores or whatever. And so processes is a software idea. It's a separate little program running in its own little memory space. And MPI can communicate between those, which means theoretically, we can have no problem starting on your laptop a 100 process MPI program. Now, in reality, that's not going to buy us a speed up, because if you only have 4 physical cores on your laptop and you run 100 processes, they're just going to spend their time swapping in and out. And while that's fine for your normal laptop, your virus checker and your window browser and a lot of things in the background can swap in and out, and you're happy with that. For scientific coding purposes, that doesn't really buy us a speed up, right? You really only want to have as many processes as you have cores so that you can get a speed up. If you have 4 cores, you probably want to have 4 processes running your scientific code so these things can speed up 4 times. If you move that code over to a cluster and you've got 50 cores, then you probably want to have 50 processes running to speed things up 50 times. So when we're working in MPI, I'm going to make the assumption that you want to run a scientific code and you really want your code to speed up however many cores you have. So anytime I say we're running on 100 cores with 100 processes with MPI, I assume that that's exactly that one-to-one mapping cores to processes. That's how much we want to speed up. But bear in mind that MPI is perfectly happy to function like any other process on your laptop. And we started an MPI program with 100 processes on your laptop, and they're just going to all run very slow. We're not going to get a good speed up. So the default model to have in our head is we got 1 process per core. And that's because we want things to actually speed up as we run our code larger and larger. But that's not a constraint of MPI per se. Okay, so with basic MPI, we need to be able to do a couple of things to get our code off the ground. We need to be able to start our processes up somehow. Then they're going to communicate data back and forth. They're going to send and receive messages. And we'll also find as we start to build programs that we occasionally need to synchronize things carefully. And so with those 4 capabilities, we can write pretty much any algorithm. Now, MPI has a lot more routines. MPI 3 has over 400 functions in it. And so you might think that that's very intimidating. First of all, that's the number one thing that comes to mind. Oh my God, this is a lot to learn. And that's not the case at all. As we're going to see, these are large families of functions. They're all very carefully related, and they really only exist for your convenience. But with these basic 4 capabilities, we could write any algorithm. We could get something to work. So all these extra functions just make life a little more convenient. So as we go along, we'll pick them up. So by the end of today, we'll be using the top 12 or 15 MPI functions, and you'll get the idea of how everything works, and you'll be able to write very effective programs. Tomorrow in the advanced MPI talk, we're going to go over the vast majority of the remaining ones. And is that because I'm going to talk about 400 separate functions? No, it's because we're going to find out there are a lot of variations on the simple basic functions just to make life, again, more convenient when you want to do a particular task. So you don't have to memorize all 400 of them. You're just going to find them at your fingertips when you find yourself doing certain particular types of things. And this will all become clear as we step through the examples. But let's get off the ground first and use these basic capabilities to do something. And the best way to start out is a hello world program. Let's see, I've got a question up here. How does hyper-threading fit into this? So hyper-threading, I'll take a brief digression right here, although I should probably defer this to later. Hyper-threading is a technique used by a lot of modern processors, really championed by Intel for a while, though they're starting to back away from it, which is the notion that even though you've got one physical core, because in modern programs, a lot of times a core will spend its time waiting on memory access. Memory is much slower than processors in most modern machines. And so one of Intel's solutions to that was to say, well, while this core is waiting to fetch something from memory, what if it had just enough registers, enough hardware to pretend to actually be a separate process and work on a different task while it's waiting to access memory? So in other words, they took a single physical core and said, we're going to share it and have it look to the software like it's 2 cores. And that's called hyperthreading. And it's been adopted and used in various versions by a lot of different hardware architects, a lot of different CPU architectures. And it can be very effective for codes where there's a lot of high memory latency accesses. And so, and you might have a processor that can do hyperthreading right in your laptop. They're not, again, uncommon, especially in Intel machines. And so hyperthreading from an MPI's perspective, it just looks like you have twice as many cores if you enable it. It's this thing you can turn on and off sometimes in BIOS, at the BIOS level. And so if you have a machine with 4 physical cores and it's got hyperthreading, you can turn hyperthreading on. And then from as far as the software is concerned, it's got 8 cores in it. And as far as MPI is concerned, it's happy to use those 8 cores as well. But hyperthreading, sometimes you might say, well, doesn't everything have hyperthreading and use it all the time? And the answer is that the overhead of doing that switching back and forth isn't worth it for applications that don't have these high latency memory accesses. And so sometimes hyperthreading is a loss. So on bridges, for example, our nodes have hyperthreading capability, and sometimes, well, especially on bridges 1, where we turn them on and off and at different nodes, some users would prefer it and some users would not. Anyway, that's a little bit of a digression. Let's stick with the basic hello world program here, which is in any language a good way to get off the ground. Cores or our processes.
Hey, John, we lost you for about 6 seconds there.
Oh, thank you, Steve. Sorry to hear that. Don't know why we're dropping out there. Hope it doesn't continue. So with a hello world program, we want to say hello from each one of our separate cores. Or in MPI, you might call them ranks or PEs. I said that PE term is a nice generic term. It doesn't come preloaded with baggage, so I'm going to try to use PE as much as possible. So each one of our PEs is going to say hello to us. So we're going to get a hello from each one of them. That's what makes this the parallel version of hello world. Here's the code to do this. We're going to step through each one of these pieces. There'll be no mysteries left unturned before we're done. But I just want you to get an idea. It's a pretty small, basic piece of code. And like for the remainder of the workshop, we'll also look at the Fortran version of this as well. And so we'll do both. Although I make an effort to make them both look very much like each other. So whatever programming background you're coming from, even if it's not C or Fortran, I hope these codes are as understandable as possible. But they're very short here. They just have a couple of lines. In fact, most of this code is the boilerplate code just to start and stop any MPI program, with just a couple lines there to actually say hello. So let's first of all talk about the general guidelines of any kind of MPI code and the boilerplate things you're going to find. MPI, as I said, is a library. And that means that it needs a header file like any library to predefine everything. So if you're using a math library, you know you need an include file for that library. In this case here, for MPI, we have an include file called mpi.h that you're going to find in any MPI program. In Fortran, it's called mpi.f.h. And that defines everything about the MPI library that we're going to need to use. The MPI library makes it very clear what the MPI things are by making sure everything starts with MPI underscore. So it's very easy to spot the MPI calls as well as constants or macros or anything involved with MPI because they all start with MPI underscore. Easy to spot them. The C routines, MPI routines, typically return an error condition in case you want to check that. Now, most MPI routines are very reliable, and we assume there aren't errors. If we're running on a supercomputer, for example, and we send data from one node to the next, we assume that data gets there. But MPI is capable of telling us if there's a problem. It can return an error condition. Most of the time, because things are so reliable, we don't check error conditions. This is not just true of MPI. This is true of us lazy programmers in general, right? Lots and lots of libraries that you use and APIs return error conditions. And how often in code do you just not check religiously every error condition like you should? People just aren't super diligent. I don't do that in my examples here. My lazy excuse is they would just clutter up the examples. So I don't want to have after every MPI call, I don't want to have, if MPI success equals 0, not equal to 0, print MPI error. So I don't do that. You're not going to do it in your real codes. You're already not doing it with other libraries that you use. But it is good to know that MPI can return an error on most of these calls. Now in Fortran, because Fortran calls don't return values, Fortran routines are exactly like the C ones, except on the end, they have one extra parameter that'll be an error code. So wherever you see an MPI routine like MPI com rank here, in C, this has 2 parameters to it. In Fortran, it has the same first 2 parameters and then a last parameter will be the error code. And again, we're not going to check the error code typically in most of our examples here, but that's the way all the MPI routines are. They're very uniform like that. So again, we could check them all for MPI success, but we won't. Okay, so what are the MPI routines that we have involved in this particular little simple hello world code? As I said, they're boilerplate ones you're going to find in almost any MPI code. They're not particularly interesting, but they are necessary. First of all, MPI init starts everything up. As I said, MPI is a library, so up until you hit the first MPI routine, the library isn't really doing its thing. And in the background, MPI init on a cluster might start some daemons up remotely on other nodes. It could do stuff. We don't care about it because we're not responsible for it. And sometimes it doesn't. So on a system that's really built around MPI, it probably doesn't do much of anything at all. Things are pretty much ready to go. So MPI init's not very interesting, but you do have to make it your first MPI call in your program. It doesn't need to be the first statement in your program, but it does need to be the first of the MPI routines that you call. For C programmers, you'll notice that MPI init is usually past the argc and the argv routines. If you're an experienced C programmer, you already know what these are. These are the command line arguments. So any C program is capable of understanding if it was started with command line options when the program starts. Lots of programs that you use, most of your Unix commands, right, take a lot of options. This is how a C program figures out what those options are. So if you're a C programmer, you know what these are. If you're brand new to C or you're not a C programmer, you can just ignore these and just know that every C program starts with these command line arguments, and MPI init would appreciate if you pass them along in case any of the other nodes care about some of those options. You can actually, in the later versions of MPI, just put null in for both of these. I could just make both of these null and ignore it, but the standard that you're going to find in most MPI programs is people do pass them along. So get used to it. So I won't say anything more about these, except it's just every MPI init you're likely to come across will just pass in the command line arguments, argc and argv. Let's see. Sorry, where do I check the error condition again? If I wanted to check the error condition, I could say error equals MPI comrank, and then I could see what error is equal to. I could say error equals MPI init and see if something went wrong with init. So it's returned just like any other C function. It's returned as the value on the function. And these code samples do not check for these. And most of your codes, you're not going to check every MPI call for errors. It's tedious and unnecessary and unwarranted, although you can make the argument it would be, super diligent coding. Okay, MPI init doesn't do anything interesting, but you got to have it. MPI finalize likewise doesn't do anything interesting, but it shuts the MPI system down at the end. It should, empty buffers out, blah, blah, blah. But things behind the scenes that you don't care about, and it may not do much of anything at all, but it should be your last MPI call in your program. And so MPI init and MPI finalize you're going to find in every MPI program. Now, this is actually an interesting call, and it's one we're also going to find in every MPI program, and this is MPI comrank. It finds out what the rank or the address is of that particular PE. When you start an MPI program up, every PE, every core gets assigned a particular unique number from 0 through whatever, however many PEs you have. So if we have 8 PEs in our Hello World program, when it starts up, every PE is going to get assigned a number 0 through 7. And it's going to be used throughout the rest of your code when you start writing real codes as the address to send and receive messages from. And so the rank is the identity of that node. And so every MPI program has MPI comrank. And so we have that here. So we call MPI comrank to find out what our PE is. Now, when we run this program, and this is the key concept, this is the most important concept to understand with MPI. It's the one that's going to probably take most of the afternoon for you to really absorb well and quit thinking like a serial programmer. This is the most important concept in MPI. When we run the program, all it does is take and make multiple copies of that regular serial program. You should think of MPI as serial programs, just a serial C program in this case, that just get copied and run simultaneously. That's all it does. MPI run, the command that we launch our MPI programs with, that we start this Hello World program, does nothing more than start 8 copies of the standard C code. It's regular C code. There's no magic parallel commands in the C language. Everything is serial program. There are just 8 copies of it. Get started simultaneously. And each one of those 8 copies says hello to us. That's all that's going on. We have 8 serial programs, each one saying hello. Each one of them found out what its unique address is, so it knows which hello. It does say hello from 1 or hello from 5 by calling comrank. But that's all our Hello World program does. We've got 8 serial programs. They find out what their address is, and then they say hello to us. That's all there is to it. It's not more complicated than that. And it's very hard for people not to overthink MPI. That's the beauty and elegance of MPI, is it is that simple. So again, it's going to take a while for that to sink in. You're going to want to tend to think that there's some magic parallelization happening behind the scenes. And that's why I encourage you to keep this picture in your head. Here's a departmental cluster. Lots of people build computer clusters, and you'll find in some closet somewhere or some storage room, you see a cluster like this. So here's a cluster of, in this case here, where we have 14 nodes. So we've got 14 nodes in a cluster. And when we run hello world, all that happens is our hello world program gets copied. When we type MPI run, that's the way we launch an MPI program. And we say we want to run this on 8 nodes at runtime. We say how many nodes you want. MPI run -N8. And it's going to run our regular serial program on 8 of those nodes. And so 8 of these nodes are going to say hello to us. That's all that happens right here. And you should keep that picture in your head again, that you're using just a serial program running across a bunch of separate independent nodes. That will not steer you wrong, and it's absolutely accurate. Okay, does any implementation of MPI actually use the command line arguments passed via MPI init? Lots of MPI programs do. So MPI programs, so to go back to this. So MPI programs, the whole reason that they pass this along, MPI programs like options too. And so if an MPI program is running and, and say you're running your weather model, and one of the models, when you say your weather program is called, weather, and when you run it, you can say the dates you want to run. You want to say weather from September 11th to September 12th. Those are command line arguments, and all the nodes might like to know about it. And so they'll pass that along to the other nodes. So it's not uncommon for something to use those arguments. Okay, so keep this picture in mind that all that's happening with our hello world program is that when you type MPI run, the code gets copied to some subset of the nodes, 8 nodes in this case here, and they each say hello, and here we go. And the IO, by the way, all comes back. One of the things that MPI does for us is for standard IO, the basic input and output, it will all come back to wherever you ran MPI, you type the MPI run from. So that terminal where you launch MPI from, all the IO from any of the nodes, the standard IO will come back there. Now, in most codes, the IO you're really interested in are results that you read and write from disk systems, for scientific codes. And so they'll come and go from the disk system. But for simple things like hello and whatnot, they'll all come from the terminal that you launch the program from. So this is the key concept. This is the hardest thing, I think, for people to keep in their heads when they start writing a code, is they start thinking that there's some magic parallel commands or something, and they forget you're writing standard serial C code that just is going to be run with multiple copies. And all MPI does is allow them to communicate between each other. So we say we really run the same code on all the nodes, and people get stuck in their head then this is very limiting somehow. We're running the same code on all the nodes, and they think that means they're all synchronized, running line by line the same code. No, it's not at all the case. You're just running the same program and launching it on 8 nodes. Like if you walked around to 8 different terminals and ran that same program yourself 8 times. And each program can go off in its own very different direction. Just because you're saying you're running the same code doesn't mean that things are synchronized or are magically doing the same things. For example, our code, we could write a program that looks like this. We could say if my PE number is equal to 0, so it's the PE number is the rank, the address returned by MPI rank. So when we come back and find out if I'm PE 0, I'm going to play Space Invaders. If I'm PE 1, I'm going to crack passwords. On P7, I'm going to run the weather forecast. These are all separate subroutines in the same program. So it's one program, but the nodes can be doing drastically different things. So it's no limitation at all to say that MPI copies the same code to different nodes and starts them running. The nodes can then go off in very different directions within that same code. Now, this is a ridiculous case right here, which you're unlikely to see, but keep this in your head also as a reminder. There's zero reason why the nodes should ever be synchronized with each other or doing the same thing unless we, with our MPI commands, make that happen. So you will typically find in MPI codes a pattern that looks a lot like this. You'll have one of the PEs be special, the manager PE, and it's very often PE 0. There's always a PE 0. And then the other PEs will all be doing a lot of number crunching. So with our weather code, for example, we might have PE 0 that reads in some input from the user and writes out and lets them know how the code's doing. And all the other PEs will be 50 other PEs, might be one for each state in the weather map doing the number crunching. So this is a more typical pattern you'll find than one node's doing Space Invaders and another node's doing password cracking. But it's not the case that they're all doing exactly the same line of code at the same time. So let me emphasize that with another analogy here. You can think of an MPI program as a book that our book reading group is reading. And a book reading group is, a bunch of people get together, read the same book, and like to talk about it and furthermore. So we've got here a book reading group. They're reading the same book, like an MPI program. But I don't expect them all to be on the same word or the same line as they're reading this book, right? They're all going to read at different rates and be somewhat unsynchronized. And even on a supercomputer where all the nodes are the same type of hardware, there's no reason to think they're going to stay super synchronized. Nodes have things running in the background, they're different distances apart on networks. So there's no reason to think they're going to be uber synchronized. No reason to think they're going to be very unsynchronized. But even if they've got a simple program that doesn't branch, there's still no reason to think they're going to be in the same line. So think of an MPI program as this book our group's reading. So at no point in time are we all going to be on the same word or the same line. We're going to diverge a little bit. As a matter of fact, our books are actually like those choose your own adventure books where you get to, on one page, it might say, take the path down the cliff or climb into the well, and then if you climbed into the well, turn to page 80. If you took the path down the cliff, turn to page 72. Right, those books where you can, branch off on your own adventure. Well, that's what MPI programs typically are. You've got conditional statements that say, if I'm PE0, do this. If I'm PE1, do this. And so everybody can be in a different place in the book. There's no reason to expect we're in the same place. So it doesn't make sense to ask what line an MPI program is on when it's running. So with our 8-node, 8-PE MPI program, it doesn't make sense to say, what line are we on? You can ask what line is PE0 on and what line is PE3 on, but they can be on different lines. So that's, again, this is all related. This is a hard concept for people to get into after years of serial programming. You want to say, what line is a program on? You don't get to ask that. You get to say what line is any given PE on, because they can branch and go off in different directions. The same is also true of variables. So with our reading group, we could ask everybody to rate each chapter, make a little mark at the bottom of each chapter, what they thought about that chapter. Did they love it or not? So it doesn't make any sense to ask what the value of any chapter is. It makes no sense to say, what's the rating for chapter 2? Instead, I have to say, hey, Susie, what's your rating for chapter 2? And hey, Bill, what's your rating for chapter 2? Everybody's got a different rating for a chapter. It's the same with an MPI program running on 8 different nodes, right? Different PEs. Every one of them has a variable X, for example. X can be different on every one of those PEs. So it makes no sense in an MPI program to say X, in your head say, oh, X is equal to 2. No, which PE are you talking about? So this analogy, again, will never steer you wrong. Keep this in your head as you're doing MPI programming, and it will help sort things out. Because it's very hard to overcome the tendencies from years of parallel or serial programming to not just think X has a single value. No, X has 8 values in this case. Very last thing before we move on here, talk about running these things and compiling and everything else, I want to point out is the one mystery thing, if we go back and look through our code, is this parameter right here on comrank. I said comrank gives us back our PE number. I hope you're starting to understand what that means. It tells us we're PE0 or PE3 or PE7. But there's one other parameter to it, this comworld. And this is a communicator parameter. If you look in the documentation, it'll say the first parameter is the communicator. What is a communicator? It's something that pops up again in many, many of the MPI routines. It's going to come up again and again. And it's a little fancier, more advanced feature that we're going to defer using until tomorrow, but I can tell you basically what it is now. In MPI, we'll often find it convenient to break up all of our PEs into different subsets. With our weather code, for example, if we're doing global climate modeling, we might have some PEs that are doing weather modeling on the land and some PEs that are on the ocean, and they use some different algorithms. And so we might want to break up our 100,000 PEs into 60,000 ocean PEs and 40,000 land PEs, for example. MPI makes it very easy to break PEs up and treat them as different groups. And it does that with the communicator. That breaks things into different groups that can communicate with each other separately. And so we'll find that that's very helpful. Tomorrow, when we do more advanced stuff, we'll start to use communicators. But a lot of times you don't care about the communicators. Our Hello World program, we just want all 8 PEs to say hello. That's true of a lot of programs. A lot of times in your program, you'll just want to use all the PEs. So when you're using all the PEs, you don't want any particular communicator. So in that slot, you can put in the built-in MPI ComWorld communicator. So this is a predefined one in MPI that just means use all the PEs. And that's a very common one. A lot of times you do want to use all the PEs. Tomorrow, again, we'll get into some subsets and we'll see how we might want to only, do things with parts of, some subset of PEs, but we're not going to do that just yet. So we'll stick with MPI ComWorld. And that means all the PEs participate. Okay, so that's our little program. if we've got an MPI program, we want to compile it. We're dealing with Fortran and C and compiled languages, so we want to compile things before we run them. As I said, we're using normal compilers, C and Fortran compilers, but MPI is nice enough that when you install MPI, it will usually also include, bundle in a little MPI specific wrapper around the compiler so that we don't have to worry about including the libraries. We could skip this. So on Bridges, you could type cc-l MPI, that means include the library MPI, and and things would work. But again, MPI installations usually to make life easy on you include a nice little wrapper, so we can use MPI CC or MPI F90 for Fortran codes, but don't let this fool you into thinking you're using a special compiler. Behind this is the generic, in this case, NVIDIA compiler, or we could switch over to a generic GCC compiler or Intel compiler, but whichever compiler you're using, it's nice to use the MPI wrappers. But these are standard compilers. Please don't let the use of these wrappers make you think you're using a special MPI parallel compiler. Not the case at all. And when we compile things here, our default executable will just be a.out. That's the name that most compilers spit out if you don't give them a special name to use. Okay, so here we've got our hello world program. We saw the code for it. We'll go back and take another look at it now, but we saw the code for it, not a big deal. We compile it with MPI CC or MPI F90, depending on whether you want to compile a Fortran to the C code, and then we run it. At runtime is when we decide how many PEs we're going to use. So the nice, properly written MPI codes don't predefine how many PEs they're going to run on because they like to be flexible. It's nice if you've got a program that can run on your laptop, but can also run on a supercomputer and can scale up or down to the number of PEs that are available. The weather code, for example, you might want to do some development on it and just, work on your laptop or your departmental workstation at night while you're improving the code. And then you release the runtime version to the supercomputer for the National Weather Service to use. And it's going to run on 100,000 PEs tomorrow. So it's nice that the program can, run on any size machine. And MPI run allows us to do that. We got the same a.out we can drag around. But when we run it on 8 PEs, we can fire it up on 8 PEs, and we can take that same a.out and run it on 2 PEs, and it'll work just fine. It'll just say hello from 0 and hello from 1. So we don't need to recompile in order to run on different numbers of PEs. We get to do that at runtime, and that's what MPI run does. Okay, so here's the process. This is a good time to start asking questions if you don't get how we get from here to here. So we've stepped through all the pieces of how we write. This is the C and Fortran version of the code. This is the very simple C code here. It does nothing more than call MPI init to set MPI up. It calls MPI comrank to find out what the PE number is for each of our PEs. And then each one of them will print out what it is and call MPI finalize to quit. And then we compile that code with MPI CC. We run it with MPI run. And here's our parallel run and its output. So make sure you're comfortable with this step right here, because we're going to just build upon this foundation as we go. So don't get left too far behind. Although along with that caution, I'll say at any point in time, I'm happy to step back and go to prior material. So as we get more advanced and we build on things, if you recognize that something earlier isn't quite clear, don't hesitate to ask me to go back to an earlier slide. I'm happy to do that. But it's good to keep up. So if this makes sense to you, great. If it doesn't, this is a good time to ask some questions. So let's see what we have here. The bottom box is pseudocoded the above. No, the bottom box is Fortran and the top one is C. So that's why they're two separate codes. So this is Fortran and this is C. So if you pick one and just stick with it through the rest of the day and tomorrow, you're going to be in good shape, and unless you're interested in both languages. But so this is C code, and it's not pseudocode at all. It's absolutely working C code. You can cut and paste and run, and this is absolutely working Fortran code. Let's see. This MPI run, we'll find 8 PEs, copy the code 8 times. Yes, so your comment, I won't reiterate the whole thing, is very much correct. If there are not enough nodes available, we'll throw an error. Yes, it would. So depending on how your system is built and installed and how people like to report errors, so on Bridges, for example, if you try to do MPI run with more cores than you've asked for with Interact, it will tell you. So you don't have this many cores. So that's the typical way it'll behave. People who install MPI, you can set things to behave differently. Are lower and uppercase is different? No, all of my examples should strive to be very much exactly the same. So with the C and the Fortran codes, I have strived to make them as similar to each other as possible with the same output, the same results, and line by line, they should pretty much be doing the same thing. And so that's what you'll see. And you'll notice the exact same MPI calls, the same parameters, the exception being, as I mentioned, Fortran has one extra parameter for the error code stuck on the end, whereas C will return the error code as the function value if you care to check it. When we're using MPI run-N8, we are giving APEs to work on. And the program for choosing N, how does that work? So the user who runs it chooses N when they run the code. So think of it that way. The user chooses at runtime how many PEs they want to grab and run this MPI code on. So MPI run is the user's choice, and it's that simple. It's the user's choice. Let's see, you're passing in memory addresses to your MPI routines. Fortran, you're passing in just a variable. That is specific to the language. So in C, if you're a C programmer, I hope you're comfortable with the notion of pointers. We give a pointer to our data structures. And we'll see this will become clear as we start to actually pass real data around. Fortran doesn't use pointers by default. It is there in the language, but it's a kind of esoteric feature. And so Fortran, we just give it the name of the variable straight up. So that is a difference you'll notice, is that we use this ampersand to point to give the address into the MPI routines for C. Okay, let's actually do some message passing now. Our hello world program is a good introduction, but it doesn't actually do any message passing. And it's now, let's start to send some messages. We're going to write a program that's going to run on 2 PEs. And it's going to send a very simple message, which is just going to be the integer 42. And it's going to send us from PE1 to PE0. And then PE0 will print the number out. So a very simple little program, but it will actually do some message passing. And we'll also get introduced to the idea of looking at the MPI documentation, because you'll find it very useful to have it when you're an MPI programmer, to have open next to you in your code window, is to have a browser window open pointing at the MPI docs. And I'll give you some good manuals. There are lots of different ones. MPI is very mature, so there are different documents out there, and you can pick one that you prefer, but this happens to be just one of the ones I have out of the list, and it lists all the parameters for the MPI routines. And that's maybe the #1 thing when you're doing MPI programming. The MPI routines have a fair number of parameters, and they're very repeatable from one version of a routine to the next. So quickly you kind of get the idea of what they are in your head, but it's nice to verify things and have a browser window open, especially since you're new to all of this. So it's good to have documents to tell me explicitly what each one of these parameters are. So in this case here, we're going to do some message sending. So we want to do an MPI send. And that means, when we look at the documents here, the first parameter is going to be the variable we want to send. And it's number to send. This is the C version of it, so with an ampersand. If this were Fortran, we could forgo the ampersand. So we want to send number to send. Now in MPI, it's important to keep track of the types that you're sending, because they take different numbers of bytes and everything in the messages as they go along. So you need to be clear about what types you want to send. I said we want to send an integer here, so we want to send 1 integer. By the way, that count of 1 integer, the count is another parameter that in MPI is used a lot. In our case, we want to send 1 integer. You might say, why would you want, what does the count mean explicitly? It means we might want to send an array of integers. We might have an array of 1,000 integers, in which case we could say 1,000 here and point it to an array of 1,000 integers. In our case, we just want to send a single individual scalar. Scalar is a term you hear in programming a lot for when something's not a vector or an array. We want to send a single scalar, a single integer. So we want to send 1 integer. Where do we want to send it? Well, in MPI, we use the PE numbers, those numbers that everybody gets assigned when they call com rank. And we want to send a message. We said in our problem, we specified we want to send a message from 1 to 0. So our destination parameter is PE0. This is where the message is going to go. Now we have one more feature that in MPI is used quite a bit, and it's also ignored quite a bit, depending on how convenient it is, and that's a message tag. A tag is a feature that MPI allows you to use to sort between different types of messages. You can have a lot of different messages in flight in MPI code. In our weather code, for example, we could easily be sending around temperatures, wind velocities, humidities, barometric pressures. You get a lot of messages flying around. You might find it helpful to sort between them by tagging the messages with different types. And so an MPI tag is built into every MPI message. And if you don't want to use tags, a lot of times in your algorithm, you know what you're sending. You say, I just want to send a message to my neighbor to the north, and we all know what this is. We're not mixing messages up. So just leave it equal to 0, and that's fine. That'll work. Sometimes, though, you do want to sort them, and you can use integers to sort between them. So in this case, I stuck a tag of 10 on this message, just to distinguish it. It won't be so important in our simple case here. But again, if we start having lots of messages fly around, it can be a nice way to sort things. And the last parameter is that communicator I talked about before. If we were using a lot of different subsets of PEs, this would be maybe useful to keep track of things. In our case, we clearly are not. We just have two PEs involved and we're sending a message between one and the other. So whenever you don't care about the communicator, you can stick in this predefined MPI COM world. It just says, use all the PEs. We're not going to sort any of them. So this is the MPI send routine. The MPI receive routine that you want on the other end looks very, very similar. That's why I say cut and paste is your friend here. It's a good thing to do when you're writing code. If you do this MPI send somewhere else in your code where you want to receive messages, that type of message, that particular message, you might want to just cut and paste your send and edit it a little bit. And you edit it into a receive. And your receive command has a variable you want to receive the message into. Again, it's in C, so we'll use the ampersand to give the pointer to that variable. You better receive the same type that you sent. That's why cut and paste is also helpful. I sent one integer, I better be receiving one integer. I can receive from a particular PE if I want to be picky. I can say only receive a message from, in this case, I could say only receive a message from PE1, and that'd work just fine because I know my message is being sent from PE1 to PE0. Or I can be a little bit more promiscuous and I can say, hey, receive a message from any message that's pointed at me I want to receive. And this is kind of the wild card in MPI. It's a predefined thing called MPI any source. This will say, just grab me the message from anybody. Likewise, I can filter on tags. The tags could be very useful to me because I got a bunch of different messages coming in. At the moment, I just want to receive barometric pressures. But in this case here, I'm not going to use tags. I just want to receive any tag. So I don't really care what the tag is, just receive anything. We also have the communicator once again, we don't care so much about. And the last parameter up here on the receive is one we have to add in instead of we have on the send, we have to add it in here, and that's the status. Status set is a little structure that has some information about the message you received, like, for example, where it came from and what its tag is. Because maybe we didn't sort on it, we didn't filter on it here, we just received the message from any source, but after the message comes in, it might be important for us then to check and say, where did it come from? We might be receiving a message from all four of our neighbors. We just want to get the next one waiting for us. But then we need to know whether it came from our neighbor to the north or the south or the east or the west. So we could check status afterwards. So that's what MPI receive is. So we put this all together now. And here's our C code. We'll look at the Fortran one in just a second. Here's our C code to send and receive that message. So once again, we've got our boilerplate standard stuff. We've got our header file here. We've got our MPI init, our MPI com rank to find out if we're PE0 or 1 in this case. And then based on whether we're 0 or 1, we can do the right thing. If we're PE0, we want to receive a message. We know PE1 is going to be sending us a message. If we're PE1, that means so if we're not PE0, it must be PE1. If we're PE1, we want to send a message. So we send this message. It's one integer. We're going to send it to PE0 with a tag of 10. What is that integer's value, by the way? Well, if we look up here, we actually set number to send equal to 42. So we have this integer 42, and we want to send it to PE0. And if we're PE0, we want to be sitting down here. We're going to be receiving a message. We want to receive this message. It's going to be one integer. We don't care where it comes from or what tag it has. We're going to receive it. And once we've received it, blocking this MPI receive will block until the message is received. So the standard MPI receive command, the one we're going to start with, is what's called a blocking receive. It's maybe the most basic one and the easiest one to kind of start writing your code with. It will wait until the message is received. There are other MPI receive routines, for example, that'll continue and say, the message isn't here yet. I'm going to go do something else. Well, in our case, we have nothing better to do except wait for the message because we better wait for it before we print it out. So our receive will sit here and wait until the message comes in, and then it will print the result out. Got a question pending, but let me cover the Fortran code first since it's exactly the same thing, and I'll go back and cover the questions. So this is the Fortran code right here. It does exactly the same thing. It basically has a boilerplate code called MPI init to set things up, com rank to find out which PE we are. Here's our number to send, it's 42. If we're PE0, we want to receive a message, one integer. And if we're PE1, we want to send this one integer. Now let me ask for either the Fortran or the C codes. This number to receive right here, I said it's a blocking receive. When this receive is reached by PE0, is this message here, is it ready to receive? Is the message, is 42 already sitting here and the receive can go right ahead? Or is receive blocking and it's going to have to wait a little bit for the message to get here? So I won't overwhelm the chat channel with responses, but I'll just ask you to ask yourself, Is receive going to be blocking, or is it going to be ready to go when it gets to this point in the code? Is the message here already, or is it ready to go? I'll give everybody 5 or 10 seconds to think about that. And the answer is, and for both the Fortran and the C code, I'll go back to the C code just because, the answer is you don't know. When we get to this receive right here, the message might already be there, might not be. There's no way to tell from looking at this code. Remember, this is running on 2 separate nodes. It's the same serial program running on 2 separate nodes. Maybe PE1 is really fast, got down to here, sent the message, the network's fast, and it's already here. PE0 is waiting for it. So when PE0 gets here to receive, the message is there. Maybe it's not so fast, and PE0 gets down here first and has to wait for the message to be sent by PE1 and to make its way over the network and to be received. There's no way to know. And it doesn't matter because a well-written MPI program like this is always going to work the same whether the message is there or not. It's going to wait for the message to print it out, but there's no way to tell for sure. So you do not know whether this receive is going to have to block or not before it can print the number out. Not there. Make sure you believe me on that. That's an important thing to understand, because otherwise, if you start again thinking that the program is on this line and it's on this, no, you're thinking wrong. Instead, you think PE0 is doing its thing and PE1 is off doing its thing, and they're both separate, and there's no way to be sure which one gets where first. One of them could be much faster or slower than another. Okay, while you think about that, I'm going to answer the pending questions here. Let's see. One was the number of items to receive. Did I mention again, vector containing? Yes, the number to receive here. We'll get on to some vectors later on and some arrays, but if we wanted to send a whole array of integers, say we had an array of 100 integers, then we could say, point at the array and say we want to receive 100 integers, and then you can receive a whole array at once. In big codes, in real scientific codes, an awful lot of what you want to send around is big chunks of array. In our weather code, for example, we don't want to send one pressure from Pennsylvania to Maryland. We want to send a whole big strip of data along the entire border. That might be a whole megabyte worth of data about pressures on that border. That's the message, would be a megabytes worth of pressures that we send. So it might be 100,000 elements. And so very often in MPI codes, you want to send more than one integer or one floating point value. You want to send a whole array or chunk of an array or multiple arrays. And so in our case, though, we just want one integer instead of an array. And we'll get to some of those examples for sure as we make more complicated codes. Can you send messages that are generally available to all nodes? Yes, you can. You can broadcast messages. That's a new MPI routine we haven't gotten to yet. But the send and receive are point to point. So you'll see that that's the actual terminology you'll see in the documentation. So send and receive are point to point. So they are not, they go between one PE and another PE. But sending messages that are broadcast, all the PEs, is a useful thing to do as well. And we'll get on to that. But that's MPI broadcasting. These are point to point. Let's see. Why C version doesn't specify PE1 to send the message. Let's look at the C code here. Because it's the other end of the else statement. So if we run this on, I'm assuming we're only running this on 2 PEs. And so PE0 receives the message. That means the only other PE is PE1 to send the message. So I'm assuming we're only going to do MPI run on 2 PEs. So it's kind of implied here. It's implicit. But we could put in, to make it a little more like the Fortran code, we could write if my PE number equals 1, then do the send. That actually might not be a bad idea, and that this code would work better if we ran it on 10 PEs. If we ran this code on 10 PEs accidentally, what would happen? Actually, 9 PEs would try to send a message to PE0, and it would only receive one of those random 9 messages. But I'm assuming this is only running on 2 PEs. So that's why I can get away with this kind of simple-minded logic. In Fortran here, I decided to be a little more explicit with the logic. I understand that if we only run one process, the program would hang waiting for message forever. So if you only ran one PE, yeah. If we only ran this on one PE, so PE0 is waiting for message to be sent from PE1, PE1 is never going to send that message. That wouldn't be solved by switching the sending and receiving branches. Wouldn't solve that problem. If we run this on one PE, it's going to hang, and there's no real way to rewrite it, or just to rearrange this, this so that wouldn't be the case. Okay, so I hope everybody is making sense of this. If this makes sense to you, you're in pretty good shape. You're starting to really get MPI. We're going to build out from here, but this is the key concepts right here. So if these C and or Fortran code makes sense to you, you're going to be in good shape. Difference between MPI-F and MPI. So the Fortran is being a very different language, has very different header files to define everything. So Fortran's just a very different language, so it has a completely separate header file. If you look in this header file, it uses Fortran. If you look in the other header file, it's a C header file. So that's the difference between the two. Okay, so let's move on. Now I'm going to take a little bit of a detour here, and I really want to warn you this is an optional detour because people want to know what happens behind the scenes with MPI message sending and receiving. So I'm going to step you through what happens when you send and receive a message. And it's not essential for you to know this. You could just treat it as a black box. I send a message and I receive a message, and that's all there is to it. And it blocks till they've received and everything works. And you can do that. But what would happen if I do that is people will ask a bunch of questions about what goes on behind the scenes because it makes sense. You want to know how things operate. You want to know what performance implications are and how things might break. So I'm going to end up describing how things work behind the scenes anyway, whether I want to or not, because people are going to want to know. And I don't want to do it piecemeal. I'd like to do it in one coherent talk. But what I don't want to do is scare you. I don't want to frighten you right now to have you think that the details I'm about to step through are necessary for you to understand to make your MPI codes work. I'm going to explain exactly what happens when this code runs. But you do not, during the course of this detour, do not get intimidated and think you need to remember all of these details. If you don't know any of this little detour section here for the next, I don't know, 8 or 9 slides, you're fine. But I am going to explain what happens when we send and receive messages, and it'll be very helpful to you moving forward. But don't get bogged down. Don't get bogged down. So we're going to peek behind the curtain a little bit here. Let's see. I'll answer a couple questions here that just popped. Do MPI only work for C and Fortran? C and Fortran are the official MPI languages that they work directly with. Now, because MPI is so important, all the many other languages, like I see people asking about C++, for Python, MATLAB, R, they all have wrappers to interface with MPI. And we'll talk about those in the advanced talk tomorrow. I'll talk a little bit more about Python and C++ in particular, since those are the most common. But the official languages that interfaces with is C and Fortran. It used to be C++, used to be the third one. I'll talk about why that got dropped tomorrow. But C and Fortran are the official ones. If you look in the documents, the standards, that's how things work. But then other languages will have wrappers to make it work with, like Python, for example. Most of the libraries used in Python, like NumPy and whatnot, are written in Fortran and C, and there's a library to wrap with that. The same will be true here with MPI. So we'll talk about that, but I'll defer that till tomorrow. But there's a reason we're focusing on Fortran or C, and that those are the absolutely official ones that are written directly. So things that use MPI write directly with Fortran and C. That's how they implement things directly, and other languages can piggyback on those. Okay, so we're going to get behind the scenes a little bit. So when we send a message in MPI with an MPI send and MPI receive, here's what happens. Now I'm going to talk about the case where we're actually sending an array, because that's the more interesting one. We're not usually sending in real codes a single integer or a single floating point number. We're usually sending a big chunk of data. Again, in our weather code, we really want to send a big chunk of the map. So we're going to send an array. So I'm going to talk about an array here of data. And what happens when we send an array is that our MPI send copies that down here into a send buffer on that same node. So on the node, the data gets copied down here, waiting to be sent, waiting till it has time on the network that it could be sent. So that's what MPI send does immediately. Now, that copy is a little bit expensive. You got to copy a bunch of data, and you got to have the space to make a copy of data. So you might say, why make a copy? Why not just send it directly from memory? And the reason is because after we send this A array here, we can go ahead now and immediately start to operate on the array. So we sent A, we now know that copy is safe on its way. We can go now and do programming. We can do math operations and our weather map. We can go and start working on the next time step in our array, knowing that we sent our data on its way. If we tried to send the array directly out of memory, we would have to pause here and wait until the entire thing gets sent over the network over to here before we can mess with it. So to make life simpler for us, we can do a send and then forget about that copy and be on our way. We can go mess with A now after our send command. So that's the reason that the default MPI send makes a copy down here to be sent. It says, well, you can immediately then forget about that copy and go work on your data. And in an algorithm, a lot of times, that's the simplest way to work. It's like I updated my array, I got my new weather data, send this to my neighbor and I'm going to start working on the next time step, instead of having to worry about whether my neighbor got that copy yet before I can touch anything. So that's the reason that send makes that copy. So the copy's sitting there in the buffer, and eventually A will get copied over into the receive queue, wherever we send it to. And that will sit in the receive queue, and it will sit there as long as it needs to until the receive queue, the program running the receive queue, has the time to do a receive. And it will eventually do a receive, and it'll be received up here. And so it won't stick it right in the memory, because that program might have been in the middle of working on another time step, and we can't just overwrite data. So this send and receive process that we use in MPI with blocking sends and receives is the simplest way to program. We'll find it makes it very simple for us to think about our data. We send some data and then we receive data. We're in control and we know where the data is. It's not the only way in MPI. We'll find out MPI has alternative mechanisms that are more efficient or allow us to do other things. But the blocking sends and receives that we're using right here are the most basic ones. And there's a reason for that. It keeps life simple. So that's what happens when we send and receive messages. Everything happens in the background. We don't worry about it. Now, in the background, messages might be piling up in your receive queue because a lot of PEs are sending you a lot of different messages. So when you do a receive in MPI, there's a reason that you might want to pick the message you receive, because your receive queue could have a bunch of messages stacked up in it. And so here's a bunch of data piling up in PE0, for example. It's got all these messages piled up that came in from different sources and had different tags. So when we do a receive and we say we want to receive a message from source 1 with a tag of 2, it's going to go through this queue and look for the first message that hits on it, which happens to be 444 from PE1 with a tag of 2. When we say we want to receive from 3 with a tag of 2, it's going to start going down through the queue, and there might be multiple messages from 3 with a tag of 2. There are, and it'll grab the first one that came in, 1008. It'll grab that message, and this one will still be sitting in the queue waiting for the next time I try to receive a message from 3 with a tag of 2. So the messages pile up in the queue, and when you do your receives, you're basically filtering on those messages and selecting which ones you want to receive. And so MPI doesn't guarantee you anything about the order in this queue, except that messages from the same PE, so all the messages from 3 will at least come in the order that 3 sent them. So if we look at the messages from 3 and we will go back to 3 and say, what order did you send them? This is the order that they came from 3. But along the way, messages from other PEs can get mixed in on the network and leapfrog each other. And so they all pile up in the queue. And you, when you do the receive command, choose which one you get. So what if we do a receive with a tag of from a source of 4 with any tag? Well, it'll go into this queue and it'll say, you got lots of messages waiting, but you know what? None from 4 yet. So it'll block and it will wait for a message from 4 to come in, even though we've got lots of other pending messages. So your receives will block until one of the messages in the queue matches what it's looking for. So that's how you should think of the messages piling up. Now, there are non-blocking sends and receives. We're going to find out these are very useful too. They don't wait until a message is there. If you do a receive and there's no message waiting, it'll say, hey, no message, and continue on the way. If you do a send and it can't fit, it'll continue on the way. What do you mean it can't fit? Well, it is possible to send very large messages in MPI. It's common to send very large messages in MPI. In a real scientific code, you frequently are sending, again, these big multi-megabyte messages. You want to send a whole big chunk of weather along a strip of the border. And it's huge. Well, messages can be so enormous in MPI, they can't even be sent in one chunk. It's not uncommon at all. So we can have a big array A here, and we want to send it, and it can't be sent entirely as one piece. The network just won't take it. The send buffers aren't big enough. The receive buffers aren't big enough. But MPI behind the scenes will do the nice thing for you. It'll send the biggest chunk that it can over to the receive queue, and it will wait until PE1 can start receiving that message. And then when PE1 starts receiving the message, it can continue on its way. Now, until PE1 starts receiving these pieces, PE0 is going to be stuck here on the send. So the send will block until the message can get all the way through. So this is a nice feature of MPI, but it also means that messages might block once in a while if they're really big. And that introduces the possibility of what's called a deadlock. And this is a common thing in parallel programming of all different sorts, but at MPI, the one that is going to sting you most likely is if you inadvertently set up a message pattern like this, where you said all the PEs are going to exchange their border information right now. It might be a normal thing for you to do. You've got a weather code. They're all done with calculating the weather at 12:02 p.m. They're all going to exchange data. So they all try to send around big chunks of data. So they all start trying to send. So PE0 tries to send a big chunk of data to PE1, and PE1 starts to send a big chunk of data to PE2. But they're big chunks, so they're stuck like this. PE0 is stuck here, waiting to send. PE1 is going to be stuck the same way, waiting to send. So they're both going to hang on their, not hang, they're both going to block like they're supposed to on their send, which means they never get to the receive, which means they never start relieving this pressure on the send on the other side. So they're both going to sit there trying to send forever. They're going to hang. That's what a deadlock is. So we can have a deadlock occur like this. Now, non-blocking sends and receives solve this problem for us. So tomorrow, we're going to get into non-blocking sends and receives a whole lot. We're going to start using them. But non-blocking sends and receives make you think a little bit more about, did the data get there already or not? We'll talk about the responsibilities for that. So they're a little bit more effort and a little bit more coding to make happen. And if your messages aren't really huge, you probably don't want to mess with that. So we're going to start out, we're going to use all blocking sends and receives today, and it'll be fine and everything will work. And tomorrow, we're going to talk about, oh, we might want to use non-blocking sends and receives here, and we're going to see how easy it is to change from blocking to non-blocking. It's very easy in MPI, but it'll make life a little simpler to start out with blocking, and that's true of writing codes in general. So we're going to use blocking sends and receives. Everything will be simple. And then tomorrow, we'll want to worry about maybe some deadlocks. We have huge messages. And how huge does the message have to be before it causes a deadlock? That's very platform dependent. It depends on the networking cards and the buffer sizes that you set or set by default. But we won't worry about it. When we worry about it, when we worry about that situation occurring, we'll switch to the non-blocking sends and receives. A little bit more programming concern to worry about, but not that much. So we'll get to there tomorrow. But today we'll stick with the blocking sends and receives. And MPI has other ways to address this issue too. That you can change the way the buffering works with B sends and S sends and R sends, but we won't get into them because they're pretty much obsoleted by just doing blocking sends and receives. They solve our problems. So we won't mess with those, but they are there in the documentation. So that's the end of our detour. So that's what happens behind the scenes when we send and receive messages. MPI takes care of all that buffering, chunking huge messages up, blocking only when it has to. It does all of that for us, but don't think that you have to keep all of that in the tip of your brain as you're programming. Here's our send and receive code, right? It's really very simple. We send a message, we receive a message. And all that buffering and transfer stuff behind the scenes, it's nice that MPI worries about what's going on, but we don't have to. So this is send and receive. So I hope everybody's comfortable with our send and receive code. I hope everybody can look at these examples right now and go, okay, I get this. If you don't get this, this is the time to ask questions. So let me see, we have a few pending questions here. MPI bindings. Yes, tomorrow we'll get into other language bindings. And R actually has direct MPI bindings. So people write R codes with MPI bindings directly, but it can be used, it is used by things as behind the scenes for a lot of libraries too. But we'll talk about that more tomorrow. Okay, so if everybody's comfortable with that example, we're going to move on to something just a little bit more interesting, starts to actually do some computation, some work for us here. And introduces the last piece of the puzzle I mentioned you need to know to do parallel programming, which is synchronization. We'll see why that's important. You can't just send and receive messages. Sometimes you actually do have to get all the PEs on the same line of code. As I said, as an MPI programmer, you don't want to ever think things are all executing the same line of code. They could all be different speeds. Sometimes you do want them to be at the same place. You need them to be at the same place. And we'll see how to do that. So this is going to be our last example before we're going to start doing some real number crunching, actually. So this one right here is going to do what are some basically kind of pointless operations, but exercise and illustrate all these concepts for us. We're going to have PE0 is going to send a number to 3 other PEs. It's going to run in 4 PEs. They're each going to multiply that number by their own PE number, and then they'll print the result out. And we're going to make them print out the results in order. Remember, our Hello World program doesn't print out in order. You know, it's just whichever PE got there first. There's no reason why any PE should get there before another PE. So our simple Hello World program, if we run it one time, it might say hello from 2 and then 3 and then 0. If we run it another time, it might be a different order. And that's exactly what we should expect out of MPI. But we're going to make things happen in order this time with our synchronization command. So we're going to print the results out in order, and then they're going to send their results back to PE0. It's going to print out the total sum of all those numbers. So we're going to jump through some hoops here just to show that we can make things work how we want them to work. But they're also going to illustrate some important general concepts. I've left them very shady here. You can barely read them because we're illustrating later on. We're going to get into this example is going to lead us directly into broadcasting. Somebody already asked, can we send a message to all the PEs? Well, yes, we can with broadcast. Can we print things out in order? Means we're going to have to synchronize things. We're going to need a new MPI command called barrier. And when we go and combine the results at the end, that's actually a reduction operation. So we're getting into the more sophisticated and elaborate parts of MPI, but we're going to do it in a gentle, gradual way by just doing the most obvious thing we can here in this example here. So let's step through it and see what I'm talking about. So here's our C code, and we'll do the Fortran one as well. So here's our C code to do what I just talked about. This implements all the steps. Let's step through them one step at a time. Okay, well, with the C code, we're going to step through the manager. As I said, a lot of codes in MPI will kind of organize themselves into this manager worker kind of pattern, where one PE is kind of in charge and all the other PEs do the work. And so we're going to find our code does this naturally here, because we're going to have one PE send a message out to other PEs. That one's going to send a message out is going to be PE0. So it's the manager here. It's the red code. The worker is going to be the green code. So we'll skip the boilerplate stuff. I assume by now people are comfortable with the MPI init and com rank. They don't do anything different here. But PE0 is going to start off by sending 3 messages out to the other 3 PEs. So it's got a little loop here. It's going to send a message to PE1, 2, and 3. That message is going to be one integer. It's this number to send, which gets set equal to 4 up here. So it's going to send a number 4 to PEs 1, 2, and 3. We're going to send them with a tag of 10. I don't think we really care about the tags right here, but that's what the message goes out. The other 3 PEs at the same time are going to be trying to receive a message, one apiece. They're going to receive into this number to receive variable one integer that comes from PE0 with a tag of 10. So that's what the first step is. That's what we wanted to do. Have PE0 send messages out to the other 3 PEs. The next step, we said we want each one of the PEs to calculate its own result by multiplying its PE number times the number it received. So PE1 is going to receive this number 4 and multiply it by times 1 and get a result of 4. PE2 is going to receive the same number 4 and get a result of 8. And PE3 is going to take that number 4 and multiply it by 3 to get a result of 12. So we're going to have 3 different results here and our 3 different PEs. Okay, that was the second thing we wanted to do. The third thing we wanted to do was print out the results in order. Well, that's going to take some thought here. It's going to take actually a new capability here. Because if we go back to our Hello World program, our Hello World program wouldn't print things out in order. So here's a little pseudocode of our Hello World program. So this is just some pseudocode. It's not real valid Fortran or C code, but it gets the point across here. So what if we wrote a code, an MPI code that looked like this? If my P equals 0, print hello from 0. If my P equals 1, print hello from 1. If we wrote a code that looks like this, would these results print out in order? Well, let me actually, I'll take a vote on this. Let me pull up the participants window here. So you can give me, I guess, a thumbs up or a thumbs down if you think this would print out in order. Give me the thumbs up. I'll give everybody a minute to think about it. So the answer is that these will not print out in order. We're not guaranteed to have things print out in order. And the best way to look at this is to think of our 8 PEs. Maybe one of them is literally 1,000,000 times faster than another. Or one of them is 1,000,000 times slower. That's perfectly possible. MPI doesn't tell us anything about what's going on in the different nodes. One of them might have some virus that's running. Somebody might be doing crypto mining on one of them in the background. It's really slow. MPI, you can build clusters out of different types of nodes. People used to do that a lot. They'd grab all their old computing equipment and build a compute cluster, and there'd be many generations of hardware. You still occasionally see that. So one of them might be much faster than another. So things could be, so PE0, for example, could be very, very slow. PE3 could be very, very fast. PE5 could be pretty slow. So when this actually runs, the results could be in any order. We don't know. But let's say we had a new MPI command at our disposal called barrier. And barrier basically says every PE has to get to this barrier before any of them are allowed to continue. Barrier, by the way, is a concept you'll find across all different types of parallel computing. So you've done any other parallel computing, you've seen the term barrier before. But barrier in MPI means explicitly all the PEs need to get here before any of them can continue. It's like in our book club. If we go back to our book club, it's like I said, we're all reading through the chapters. I said, everybody stops when you get to chapter 2 because we want to talk about chapter 1. So it's exactly like that. So we got fast readers in our book club. We got slow readers, but everybody stops when you get to chapter 2 before we continue. So even though the fast reader got there first, they have to wait until we can continue. So in this case here, with barrier, with barrier, with this code, print in order. Go with the thumbs up if you think it would print in order. Well, everybody's guess so far is correct. This will actually now print in order because it doesn't matter. We said before, we said, maybe PE2 is very slow and PE5 is very fast. So they start running this code and PE5 just tears right down. They all print 0, 1, 2, 3 print, and they all get down here, and PE4 wants to print. PE5 wants to race ahead, but it has to wait for PE4. Even though it's very slow, it has to wait for PE4 to get to this barrier before they can continue, and then PE4 gets to print before PE5 can print. So the barriers make sure that even if one's a million times faster than another or a million times slower, this will always happen in order. So that's why barriers are very useful at controlling things. And if we're smart, we'd roll this into a for loop. We don't want to write our code out like that. Instead, we just put this into a loop. So here's a loop that does exactly that same thing. It just basically makes sure that no matter how, we'll put a barrier in the middle of the loop. So no matter how fast or slow any PE is in trying to tear through this loop, PE0 gets to go first, and they all have to wait at the barrier for PE0 to get here after it's done printing. And then PE1 gets to go next. So even though PE5 is super fast and races ahead, it's stuck waiting for PE1 to get to the barrier to continue, and PE1 gets a chance to print. So if we stick this barrier in the loop, then we can force these hellos to print out in order. So that's exactly what we're going to do. Now, here's a little side note. I don't want to spend too much time on this, but I'm going to mention that when you start doing, start putting print statements in and having things race each other and whatnot with MPI or any parallel system on big machines, sometimes you will find that your print statements get a little more mixed up than you think, or sometimes they don't even come out until the program's done running. And this kind of confusion is caused by buffering in the system. Modern computer systems buffer everything silly. Buffering helps performance a whole lot. So with your laptop, if you're writing stuff out to disk, say it's just keeping track of your history as you're browsing, and the browser's writing stuff out to disk, to a disk file. Instead of it writing every single byte out or every little entry out at once, modern operating systems try to bundle a bunch of writes together in memory, and then it'll write them all out as a chunk. It's going to be much more efficient and much faster. So there's lots of buffering goes on all over the place in modern computers. And that's fine, and it speeds things up a whole lot. You wouldn't want to turn that off. Things would come to a bogging halt. But when you're using print statements in your code to debug stuff, which is a good beginner way to do stuff, it can be very frustrating. So if you're a beginner and you're sticking a lot of print statements in your MPI code to figure out where you are and which different PEs are doing what, sometimes that buffering can get in the way. Now, I'm going to talk about debuggers tomorrow and ways to debug your code that are a little cleverer than using print statements. But print statements still a good way to go, and many of you are going to use it today for our basic exercises. And I still use print statements frequently to figure out what's going on in the code. So here's a little trick that's very useful whenever you're using print statements in modern machines, and you think that maybe it's buffering stuff and it's not spitting the print statements out as soon as it hits them in the code. And you can turn off buffering, and many of you might think, actually, if you're more advanced programmers, you might see that there's flush commands in modern, in computer languages. Flush is a command that usually says, I want to flush all the IO out and make sure that things don't buffer. Sadly, most modern operating systems don't care about flush commands. You can issue the flush command and they just totally ignore it and things get buffered somewhere else downstream. So flush doesn't work as nicely as you might like. Here's a trick I find to be very useful, and that is to write the standard error instead of standard out. So most programming languages and operating environments, runtime environments, have a standard output where output just goes by default, usually comes back to your terminal. And they also have this error output, which is where you're only supposed to write error messages and things that are of that nature and that priority. Well, if you write to the error stream, it usually is not buffered. And here's a cheap and dirty way to write to the error stream. So I include this here because those of you that are going to pursue parallel programming and are going to occasionally use print statements because you don't want to fire up a debugger to debug your code, sooner or later, you're going to get upset because I said print when I get to the subroutine, and I got to that subroutine, and where'd the print statement go? It didn't come out until till later. You're going to find this to be a very useful little way to force prints to happen when they should. So anyway, hate to take that digression, but this is the right place to stick it in. So in our case here, we now have our barrier command at our fingertips. So we decided we wanted to have our output come out in order. So we stick our barrier command in a little loop here that prints our output. And this will make sure that no matter what happens here, when PE0, well, PE0 is actually the manager. So when PE1, it's turned to print the output here. When PE1 comes into this loop, PE1 is going to be able to print the output first before PE2, no matter how much faster it is, can race through the loop and print its output. So this is basically just a looped version of this. It's going to make sure that our output comes out from PE1, PE2, and then PE3. Guaranteed every time, no matter how fast or slow any PEs are. So this is going to print our output out in order, which was part of our problem statement. Okay, so what's the next step we wanted to do? We want to have each one of those PEs send its result back to PE0. So PE0 is going to receive 3 messages. Well, PE1, 2, and 3 are going to send 1 message apiece. So PEs 1, 2, and 3 are going to send this 1 integer to PE0. The tag of 10. PE0 sitting here, it's going to receive 3 integers, 3 separate messages, 1 integer apiece with a tag of 10. It's going to receive from PEs 1, 2, and 3. And as it receives each message, it adds its result into its total result. So result equals result plus the message it just received. So now we're on to our last step, which is for PE0 to print the result out. It's going to print the total out, and we're done. So I hope everybody could follow through this example with me. I'm going to step through the Fortran one once again. It's the exact same kind of code, so I'll be a little bit quicker about this. Not disrespecting Fortran people, but I figured you probably absorbed most of this pass through the C code. So I'll step through quickly, but it's also the C programmers, your chance to follow along once again if you had any confusion about the logic. Basically, we said PE0 is going to send a message out to the other 3 PEs. So it does that in this loop. It sends a message out to the other 3 PEs, and they receive that message. That message happens to be the number 4. So they receive that number 4, and then they each multiply that by their own PE number. So they get a different result. Now we said we wanted to print out the results in order. So this is where we have our loop that goes in order for PEs 1, 2, and 3 with a barrier in the middle of the loop that makes sure that none of the PEs can jump ahead. So they each get to print the result out in order, 1, 2, and 3. Then they take that result and they send it back to PE0. So each one of them is sending a single message back to PE0, who's receiving 3 messages. PE0 receives those 3 messages, adds them together, and prints out the final result. I hope you're all comfortable with this code and why the output looks like this. Every time it's going to be PE1, 2, and 3 printing out the partial result and a total of 24. I hope everybody is comfortable with this. Now, as a little exercise, I said this code only runs on 4 PEs. So I kind of violated the rule. I said good MPI codes are flexible. They can run on any number of PEs. So the user at runtime could say, hey, I'm on my laptop, only run on 2 PEs, or I'm on a supercomputer, run on 2,000 PEs. So I said MPI codes should be flexible. This code, I kind of hardwired into it, especially as we step through it. I said it's going to run on 4 PEs. So what would happen if I ran this code on more than 4 PEs? How about if I ran on less than 4 PEs? I will leave that as an exercise for you to think about, and we can come back to that in the Q&A session later for those of you that have time. I want to give you time to think about what happens if we run this on 6 PEs or 5 PEs. What happens if I try to run this on 1 PE, 2 PEs? You should be able to figure out what happens. MPI is very, very deterministic. You should be able to figure out how it will break, or will it break, or will it still kind of run the same. I leave it to you to think about that. Okay, so MPI barrier is the last piece that we needed to make our codes to pretty much write anything. Between send and receive and barrier, we can write anything we want to. We can do any kind of algorithm we really need to. Barriers are often absolutely necessary to make algorithms work. They're also very often convenient when you're writing a complicated code and you want to, just for the sake of sanity, get all the PEs on the same page before you let them continue ahead. So you can use them to debug. You can say, okay, everybody pause here. Let's check things out, make sure everything's right, print a few things out, and then go ahead. So barriers can be a fantastic way to help with debugging. If you're worried about things racing ahead and getting each other's ways, barriers can be a good way to deal with that. But barriers also take time up. Their job is to make PEs stop, to make them wait. So unnecessary barriers are wasteful. They waste time when the PEs could go ahead and start doing more useful work. So one of the things that you'll often see people doing is putting in lots of barriers to write a code and then kind of removing them as an optimization step when they're done. And they can't remove them all. Barriers are often absolutely required, but extra barriers are a bad thing. So, think of them like, I've heard people say ridiculous things like, well, just don't have barriers in your code, and I get rid of all the barriers. That's just absolutely impossible to do at times with algorithms that need barriers. But I've also seen people that, just sprinkle barriers around everywhere just to make life easier, and they don't go back later and eliminate them, and a huge amount of time can be wasted in the code. So you think of them like a race car driver thinks about brakes. You don't want to use them more required, but you absolutely don't want to build a race car without brakes either. So that's barriers. So don't subscribe to any simple-minded philosophy about use tons of them everywhere, or don't have any barriers in your code. It's never that simple. Okay, let's see. MPI, could you share a bit more about MPI barriers actually waiting? To wait for each code to get that line containing barrier. That's exactly right. So MPI barrier waits for each code, each one of the separate instances of the code to get to that line before any of them are allowed to continue. That's exactly right. Okay, you'll notice as I've stepped through these codes that I kind of think of them as I think like PE0, and then I think like PE1, and that's exactly how you should think of your MPI codes. Step through them from the perspective of each one of the PEs, or at least PE0 if you've got a worker manager situation, and one of the other PEs. You don't step through an MPI code like one line at a time, because things aren't on one line at a time. PEs are running their own way and their own path through the code. Now, with 1,000 PEs, do I go through my code 1,000 times? No, of course not. I go through it as the manager PE, typically, PE0, and then I go through it as one of the other PEs, and that's usually sufficient because the other PEs are all kind of following the same path. But that's how I do think of it. I think of them as individual serial codes, and I step through it like the different PEs. That is the way to think about and debug your codes. Do not think of it as it's a magic parallel language and I'm on this line in a parallel language. No, you're running serial code on different PEs. Okay, if everybody's comfortable with this, it seems to be. Let's see. Error occurred MPI on an all communicator. I don't know what that is. I don't know what you're running, as a matter of fact. I don't know what you're doing. So we'll come back to that in the exercise session. Remind me about your problem. Okay, so beyond the basics here are lots of another 300 and some commands. Actually, maybe close to 400 commands. So I said that sounds very intimidating, but that is not at all. The situation is not at all that you have to learn that many commands. Instead, we're going to find out that these are all just really convenience functions to allow us to make life easier than just using the handful of commands that you've already learned, which would be sufficient to do pretty much anything. So let's go ahead and see how that works. Let's go and do a real program now. It's time to do something that's much more interesting than we've done so far. We're going to do a program that finds the value of pi by doing parallel integration. And if that sounds fancy and sophisticated, it is indeed actually a sophisticated technique used in lots of scientific codes. There are lots of codes out there where you need to integrate over spaces, highly dimensional spaces and complex functions. And so doing numerical integration is a huge part of many important scientific codes. In our case, we're going to pick a nice, simple, elegant problem. We're going to integrate over half a circle to find the area so we can find the value of pi. The area of the circle is pi r squared, right? So we're going to integrate over half our circle here. And integrating over a circle like this numerically is something that you learned back in basic calculus class, when you learned that basically doing an integral under a curve is breaking that curve up into a bunch of slices like this, and then adding all those slices together. And the more narrow slices you have, the more accurate the result is going to be. If we go to the limit of infinity, we get an actual proper integral. But in our case here, numerically, we go to many thousands of slices. We're going to get a very accurate result right here. And this quadrature technique of integrating is, again, useful in many different areas. We're going to do it with MPI. So we're going to integrate half a circle to find the value of pi. Because we're doing it with MPI, we're going to do it in parallel. We can speed things up a whole lot, because now instead of having to have one processor do millions of integrations, we can have each one of them work on a separate band. So instead of say we've got 5 processors here, instead of our 10 strips that we're working with, instead of one processor having to do 10 strips, with 5 processors, each processor only does 2 strips. So this is the idea here. So we're going to write a code that can run on a user-defined number of strips. So the user can say, I want 1,000,000 strips. I want a very accurate answer. And the code will run on however many P's it finds itself on. This is going to be a nice flexible code. If it runs on 10 PEs, it'll use all 10 PEs. If it runs on 100 PEs, it'll run on all 100. So if we do 1,000,000 subscripts in here, the user says I want 1,000,000 subscripts, and we run on 1,000 PEs, each PE will only have to do 1,000 strips, and it should run 1,000 times faster than a single PE. So that's what we're going to do. Very straightforward. We're going to take this opportunity, though, to do things a little bit easier. We can do this with the commands we already have, no problem. But we're going to start to do things in an easier fashion. We're going to roll in another handful of very, very popular and useful MPI commands, ones that you're going to find in virtually every non-trivial MPI code. The first one is broadcast. Somebody already asked a while ago, said, hey, can we send messages out to all the PEs, a general message? And the answer is yes, you can. MPI broadcast does that. Matter of fact, we've already done that, but we did it the hard way. Think about our last exercise. PE0 had a number that it wanted to send to the other 3 PEs. What did we do? We wrote a little loop that went from 1 to 3 and sent that number to the other 3 PEs. Well, wouldn't it be nicer if we could just broadcast the other 3 PEs? So it's not only nice, it saves us some typing and some code. We don't have to write a for loop, but it's also more efficient. Just like giving this lecture, I could give it point to point to all of you, or I can just broadcast it to the whole audience. Broadcast is much more efficient. So broadcast is nice for you as a programmer. It's nice for the program efficiency, and it's a very popular MPI command because a lot of times one PE has something that wants all the other PEs to know about. And so in this case here, the user is going to tell going to type in how many points it would like to use, how many strips it would like to use for the approximation. So we can broadcast that to all the PEs. The user doesn't have to tell all the PEs. It can tell one PE, like PE0, and PE0 can let all the other PEs know. There is another thing that we did in our last example code that we can make simpler, and that's a reduce operation. In our last example code, we had a sum that we wanted our last little exercise. We had a sum. The other 3 PEs had numbers, 4, 8, and 12, that they wanted PE0 to sum together. And that's a very common thing to do. It wasn't well motivated in that example. It will be in this pi example. Each one of the PEs is going to have its partial sum, its slices of the circle. We want to add them all together. It's a very common thing to do. Not just sums. Sometimes there's minimums and maximums. There's a lot of times there's operations where you'd like all the PEs to combine to boil the data down to a single answer. And so we wrote a loop that did that in our last example. We had all 3 of the PEs send it to PE0, and it just added the numbers together. And that's a common enough thing to do that we can save ourselves some typing and make an MPI command to do that, MPI reduce. And that allows us to reduce a bunch of values down to 1 PE. Now, this is not only a convenience for programming, it also is much more efficient. And the reason is that if we had, let's think about if we were all together in a lecture hall and we had a bunch of numbers. Every one of you had a different number and we wanted to add them together. We could sum them together by each one of you standing up and telling me the number, and we could add them all together, like one at a time. So if there are 80 of us, we could add, or let's say that 128 of us, we could add together 128 numbers, take 128 steps to add them together. Or I could say, everybody turn to your neighbor, and the 2 of you add together your numbers. So everybody turns to their neighbor, and now we're down instantly down to 64 sums instead of 128. Okay, everybody with a sum now turn to your neighbor. Now we're down to 32 sums. Now, in 7 steps, we're down to a single answer or single sum. So instead of taking 128 steps, in 7 steps, we've reduced everything down to having one answer. So it's much more efficient. So reduce operations are not just convenient for you as a programmer, they are also much more efficient than going point-to-point communications. And reduces show up so many times in parallel computing and data analysis that you will come across it again. Again, the most common ones are sums and minimums and maximums. You do the same thing with minimum, right? If we had an audience, 128 of you, and there was a minimum, we wanted to find it, we could just say, everybody turn to your neighbor, and whoever has the minimum, keep it, throw the other number out. Do that again, keep just the minimum between you and your neighbor. So 7 steps would be down to a minimum. So this reduce operation is very, very useful. One good way to think of it in your head is you should really think of it as a binary operation. Reduce is only something you do between 2 things. You define it between 2 things, and then in parallel, the parallel system does it as much as it has to boil everything down. It's a little more advanced algorithmic way of thinking of things that will serve you well if you start using reduces in other areas of parallel programming. But at any rate, I don't want to overcomplicate things. Just think of it like I just said. All the nodes keep boiling the data down until you end up with one number. In our case of our pi example here, they're going to keep summing the strips until we're down to our one final strip sum, the area under the half circle. Okay. So here is our code. Now we're going to do one last little feature here that I think was worth its own page here. One more MPI function that's very useful, which is MPI com size here. MPI com size is something that's going to help make our codes automatically fit whatever size nodes they're running on. As I said, we're going to make this pi code nice here. It actually will fit itself to however many PEs it finds itself running on. So if it's running on 1,000 PEs, it knows to break up that integration into 1,000 different pieces. If it finds itself running on 4 PEs, it'll break it into 4 pieces. And so the way it does that is use the MPI com size routine. And com size returns the number of processors that the PE is running on. Excuse me, that the PE, that the whole code is running on. So this is basically the same number that you type into MPI run. So when you type MPI run -N8, this lets the program know that that's what you did, that it's running on 8 processors. So this is the number that the program needs to know to resize itself. So let's step through this program here, because it is simple, but yet quite powerful. So here's our pi program, and it does this generic stuff, MPI init, com rank to find out which PEs, what the PE numbers are for each PE. It does this com size to figure out how to help it later on calculate how to divide the pi up. Okay, then it does the input from the user. It asks the user, how many intervals do we want to break this integration up into? So the user can type 1,000 or 1,000,000 or whatever. And we don't want the user to have to type this into each one of the PEs. So only PE0 asks the user. So only PE0 is going to ask the user for input. So PE0 does that. And then PE0 would like all the other PEs to know about that. So we can use the broadcast command. Again, the last exercise, we had a little for loop, but in this case, let's broadcast this. So it'll broadcast to all the other PEs this number. Now broadcast, and this is a point of confusion for a lot of beginners, and it's an unfortunate part of the MPI nomenclature here. Broadcast is both broadcast and the receive at the same time. Broadcast is what's called the collective communication. This is an important term here. It's not just a little bit of jargon here. So pay attention when I say a collective communication, an MPI, means an MPI routine that all the PEs simultaneously participate in. They have to. So when we have a collective communication in MPI, it means all the PEs do that thing at the same time. The first one we actually came across here was barrier. We said barrier, all the PEs have to get to barrier before anything can continue. So you can imagine what would happen with barrier if one of the PEs branched off, took some conditional statement, branched off and didn't get to barrier. What would happen? The code would hang. All the other PEs would be waiting here at barrier for the PE to get here, and this PE would be off doing some other thing, and the code would get stuck. So with a collective communication like barrier, all the PEs have to get to that point. They all have to collectively participate in that call. Broadcast is the same thing. It shouldn't surprise you that they all have to participate in the call. But what does catch people a little bit off guard is the fact that the broadcast is used by one of the PEs to actually send the data out and all the other PEs to receive the data. So you might think, if you didn't know better, that there's a broadcast from PE0 and maybe a receive for the other PEs. No, instead, MPI sets it up as a collective. So there's a broadcast, and you have to say which PE gets the broadcast, PE0. That's what this parameter is. So PE0 sends the data out, and all the other PEs at the same time are calling broadcast, and they receive the data. So broadcast as a collective. So it's a little counterintuitive at first, but once you actually do it, you realize it's nice. I don't want to write broadcast and then receive. I just want it to be one nice statement, because if they're going to do a broadcast, they're all going to have to participate. So broadcast is a collective communication. And if we step through the parameters, it says the variable n is going to be used to send and receive the data. It's sent from PE0. So whatever n is equal to on PE0 is going to be sent out. And we're lucky. This variable is the right one right here. It's the user intervals. So n gets sent out by PE0. And at the same time, then it's going to be received by all the other PEs. We do have to say the type. It's one integer. And so that's broadcast. So again, the collective communications, the same is going to be true for reduce down here. Is collective communications are called by all the PEs at the same time. So broadcast is called by all the PEs. Now they have all the information they need to do their own slice of the integration. So this section of code right here is just a bunch of math here. It says for each PE, where should I start and where should I end? And these are like calculations I need to do to figure out the integral. So at this point, they all have a partial sum. It's called my pi. So each one of the PEs participating, maybe it's 1,000 PEs. Each one of those 1,000 PEs has a partial sum, and we need to add them all together. And again, the last exercise, we could write a for loop that says, okay, all 999 other PEs, write to PE0, and it'll add the messages together, or we can use a reduce operation. So reduce here is a collective operation. It says which PE do things get reduced onto, PE0. And it says what reduce operation are we doing? As I mentioned to you, there are different ones, sum and min and max and plenty more. You could define a lot of different reduce operations, but those are the big three. So we're going to do a sum operation. It's going to come to PE0. It's going to be one floating point number. And it comes from all the other PEs are going to reduce their my pi value down to PE0's pi value. And so we end up with the value here on pi, value here on PE0 of pi, and it can print that value out. So that's the entire code. So I hope everybody can kind of pick their way through this code, because this is an example of, first of all, the power of MPI. This is a nice scalable integrator. If you run this on 1,000 PEs, it's going to integrate 1,000 times faster than any serial code will. So this is very parallel and scalable. And we're now using pretty much the top MPI commands that you're going to come across. So you've got the handful of all the, the really practical MPI commands. You can send and receive, you can broadcast, you can reduce. We don't have barrier in here, but we've come across it. So you've got all the big MPI commands, and we're going to find out that almost all the rest of them in advanced MPI talk are just minor variations on this theme. If you understand this, so make sure you do understand this. So let's see here. When P0 broadcasts, this is also receive what it sent out. Yeah. Well, it doesn't matter whether it does or doesn't, because it's already set equal to n. So when PE0 broadcasts, it's already got this value. So let's say the user enters in 500 as the intervals. It's going to be 500 going into here, and it's going to be 500 coming out of here. So it doesn't actually matter. It doesn't actually do a broadcast to itself. It doesn't waste the time with it, but it wouldn't matter either way. It's going to be the same value coming in and out. It only changes on the other PEs. It's actually a more important question down here. When we do the sum, PE0 actually participates in this partial sum. That's why there's two variables here, because PE0 might come into this partial sum with my pi might be equal to 0.002. It's partial sum of pi, and then when it's done, it's going to have the same value in here. It's going to have the full value of pi in here, 3.14 whatever, and it's still going to have 0.002 over here. It doesn't overwrite this variable, so that's why there's two variables there. So minor detail. Do MPI broadcast and MPI reduce effectively contain a barrier? They are an implied synchronization point, would be probably the preferred way of stating it. Yes, they do introduce synchronization here, right? Because they are collective operations do imply some synchronization. They all have to kind of participate before anyone can continue on their way. And so there is an implied barriers here for collective operations. And we'll see how we can play around with that a little bit more and parse that out in a little finer detail. But yes, so collective operations do start to imply some synchronization. And so here's a couple of different resources. There's a fantastic forum here that has different MPI manuals. So if you go there, you'll find it's a wonderful thing about MPI community. It's so mature, so well supported after all these years. There's no lack of resources. So here's a good place to start to find a lot of resources. It's not the only one, but it will link you to lots of other places. I don't want to overwhelm you, so this is not a bad starting place. One of the things you can find starting here, or just go directly to it at another MPI organization, is a useful document pages. This is one that you might like. There are others out there you can poke around, but I think this might be a good beginner one. It's a kind of an index-oriented one. People often want to know if there are other tutorials and resources. There are tons out there on the web, and you'll find lots of them starting out on any of these pages. But there are a couple of good books. There are only a couple of good books. There's some terrible books, but there are a couple of good books. These two books are written by, they're kind of a series here, really, the beginner one and the more advanced one, written by some people that are very embedded in the MPI committee and development process. So they definitely know their stuff, and they're pretty well written books.